I want to spend a few minutes now talking about how quickly radioactivity takes place, or radioactive decay takes place. Define a term here called the half-life. Half-life is the time that it takes statistically, and that word's going to become important for us in just a moment, for half of a radioactive sample to decay. So in other words, if you start off with 10 grams of uranium-235, how long does it take to go to 5 grams of uranium-235? If you start off with 27 nuclei of carbon-14, how long does it take to go to, that's a bad example, 28 nuclei of carbon-14, how long does it take to go to 14 nuclei of carbon-14? Now remember, as this happens, like the 5 grams hasn't disappeared, the 14 nuclei haven't disappeared, they've just been converted or transmutated into something else. How long does it take, though? Well, on average, it takes 1 half-life. If the half-life of uranium is X number of years, then after X number of years, you'll have 5 grams left. If the half-life of carbon-14 is, I think it's 5,700 years, then after 5,700 years, 28 carbon-14 nuclei will be 14 carbon-14 nuclei, and then 14 nitrogen, or whatever transmutates into. This word statistically comes into play because you have to understand that everything we're going to do today, the rest of the day, with this rate at which radioactive decay occurs is based on statistics. It's not like we know what's going to happen ahead of time. It's rather a statistical analysis of what we predict will happen. Does anybody know why it's statistical? Why that's the best we can do? That's not just us in grade 12 not being smart enough to know the real way it works. Okay, that's, if you have a PhD in physics, it's still a statistical analysis. Why? Yes, that's the word I was looking for. It's a random process. When you flip a coin 100 times, statistically, we know we're going to be left with 50 heads and 50 tails, right? But that's a statistical analysis. Until after the fact, we don't really know what's happening. Right? We can statistically predict 50 will be left, but it is a random process. Therefore, we don't know for sure what's going to happen. Just the same as radioactivity, we know that statistically half of it will decay in this amount of time, but because it's a random process, we don't know that for sure. Make sense? Not until after the fact, at least. Now, I want to give you a couple equations. The first one you're not going to recognize, and that is not on your data sheet. But the good news is it's a pretty easy one. N, which stands for the number of half-lives, is equal to T over T1/2. So this would be the time, and this would be the half-life. So let's say the half-life is 2 years. And the half-life, by the way, can vary from a small fraction of a second to millions of years. In this case, we're saying the half-life is 2 years. 6 years have gone by. How many half-lives is that? The half-life is 2. 6 years have gone by. How many half-lives? 3. Right? 3 half-lives have gone by. It's the total, 6 years, divided by the amount for 1 half-life. 2. 6 divided by 2 is 3. Again, this equation I'm going to start because it doesn't appear on your data sheet, and it's really, really useful. The second one does appear on your data sheet, and you might recognize this one, in fact, from math class. Yes, this one. Exponential decay, exponential growth. Did it? Little n stands for the number of half-lives, of course. And a lot of times we're going to have to solve for the number of half-lives by using this equation that doesn't appear on your data sheet. Sometimes you'll be given the number. A lot of times you'll have to calculate it. N0 stands for, all you math people, the original amount. And the original amount can be measured in any units that indicates an amount. Maybe it's grams. Maybe it's kilograms. Maybe it's just a number, the number of nuclei. Maybe it's a percent. How much percent remains radioactive? Maybe it's some other strange unit that you don't recognize, like a BQ, a becquerel. Don't panic. If it's a unit that you don't recognize, then it means big N or N0. Now, if you get years, that's time. That's not big N. Right? If you get seconds, that's time. That's not big N. If you get becquerel, even if you don't recognize it, then you know that that's not time, so it must be big N or N0. What does big N stand for? Minus the subscript? Yeah, this is the final amount. And what are you going to use for units here? It doesn't really matter, as long as you're consistent. Sorry? No, I don't think so. I think, I mean, it could, but the reason that they wouldn't, I don't think, is because that would confuse non-chemistry people. Or worse, actually, it might actually confuse chemistry people. Sometimes if they do something like that, where you introduce a term from another subject, sometimes people that have done the other subject overanalyze and do stuff that that you shouldn't do, right? Try to make the question harder than it has to be. I don't think they do that, no. Make sense? All right, let's do an example. Example number 1. I want to do 2 of them today. Here's the first one. The half-life of hydrogen-7 isotope, by the way, this nucleus would not stay together for very long at all. Hydrogen-7, that is a ridiculously heavy isotope of hydrogen. Normal hydrogen has 1 proton and 1 neutron. This would be 1 proton and 6 neutrons. This would be highly unstable. And you can see that the half-life is 10 to the minus 23 seconds. So it decays really, really quickly. By the way, if you had to be exposed, like if where you live was contaminated with something radioactive, would you want it to be, would you want it to be, I shouldn't phrase it like that, but what would be worse? What would be worse? A big half-life or a small half-life? Some people are saying big, some people are saying small. Well, reality is it depends, right? If you understand that if you're able to get away and there's a small half-life, you're going to be able to return much quicker, right? Because your sample will decay much quicker. If you're not able to get away, then your exposure will be much more significant because it's going to be so quick, right? Now, if you have to be present, you're better off having a long half-life that decays over a long, long period of time. Make sense? So if you can get away, short half-life, then it's done. Come back, and everything's good. But if you have to stick around, you'd rather have it be a long half-life so the rate of exposure is less for you. This is an incredibly short half-life. This would be an incredibly high rate of exposure if you were exposed to this here. 27-gram sample decays. How much remains after 1.44 times 10 to the negative 22 seconds? This is the time, 2.3 times 10 to the negative 23 seconds. No, sorry, that's the half-life. That's the half-life. The time is 1.84 times 10 to the minus 22 seconds. And this is the original amount, 27.0 grams. We want to find out how much remains. I'm going to say n is equal to n sub 0, 1/2 to the little n. I don't know what little n is, so I'll find it over here using that equation that's not on our data sheet. We can use whatever units we want here for time. Seconds is fine, as long as we're consistent. Do that, it works out to be 8 half-lives, which means that this becomes 27 times 1/2 to the 8, not 1/2 times 10 to the 8. 27 times 0.5, little hat button, 8, what, 105? So not much remains at all. 72 years ago, the atomic bomb was dropped on Hiroshima. And there was a lot of, besides the immediate destruction and the tens of thousands of people killed, I think it was around 100,000, wasn't it? People killed. Besides the horribleness of that, there was radioactive material left over. But if you go to Hiroshima now, you don't really need to worry about that 72 years later, because although it's still there, it's decayed enough that it's relatively safe levels. Radiation you'd experience in Hiroshima now wouldn't be dramatically more than what we'd experience here. In fact, some areas of Alberta actually have quite high levels of naturally occurring radioactive material. Anybody know what it is? What? Radon gas. Yeah, it naturally occurs in the ground in pretty high quantities here, actually. That's why you see all these businesses that will bring in radon sensors into your basement and then remediate your basement to keep the radon from coming through the cracks. If there's cracks in your basement. Number 2, the half-life of polonium-244 is 8.0 times 10 to the 7 years. How much time must pass before a kilogram, this is what we start with, 1.00 kilograms, of plutonium decays to 62.5 grams. This is the final amount. Let's make this 1,000 grams. Why did I do that? Consistent units. Could I have gone to kilograms? Sure, I don't know. I find it easier to multiply by 1,000 than to divide by 1,000 for some reason, so that's the way I went. I want to find t, so let's say n is equal to t over t1 half. T is equal to n times t1 half. N, we don't know what little n is, right? Okay, so let's find it over here. N is equal to n sub 0, 1 half to the little n. How do you solve for little n there? Yeah, if you're thinking the worst, it is the worst. What is it? Logarithms. How many people? Probably all of you have learned about logs, have you? By this point. The good news is, if you're not a fan of logarithms, and I never was a fan of logarithms, never. There is a way around it. Because some people take Physics 30 in the first semester and they haven't learned about logarithms yet. They don't require, the Physics 30 people don't require logarithms to be used for any questions. So in other words, if you see a question like this, there's another way. If you want to use logs, go ahead. That's fine. If you're comfortable with it, you like logs, go ahead. If you're not comfortable with logarithms, you don't like them, then do what I'm going to suggest here now. I call it the divide by 2 method. The divide by 2 method entails creating a little table. First column is a little n, second column is a big N. After 0 half-lives, no time has gone by, how much do I have left? 62.5, no, sorry, not 62.5, 1,000 grams. After 1 half-life has elapsed, how much do I have left? 500 grams. After 2 half-lives, how much do I have left? 250. 3 half-lives, I've got 125. 4 half-lives, I've got. So little n would be 4 times the half-life of 8 times 10 to the 7 years. Yeah. 3.20 times 10 to the 8 years. This will only work, the divide by 2 method will only work if n is a whole number, right? But it will, if you have a situation like this, it will be a whole number for you. Okay, it will be, because they don't expect you to use the logarithms. Now, the way that I'll do it in class is this way, just because I figure if you are good at logarithms, then go ahead, do it that way. You know how to do it. But if you're not good with logarithms, then you're the one that needs a little bit of help, and that's why I'm going to do it like this. Now, the other way, don't worry about this, okay? If this doesn't make sense to you, don't worry about it. I'm not going to spend a class explaining this to you, but you can say n is equal to log n over n0 over log 1/2 or 0.5. If you sub those numbers into your calculator, guess what n is going to be? 4. Yeah. The green way works if it's not a whole number. The blue way works only if it's a whole number. But unless you can solve for a little n using this equation, it's got to be a whole number because they don't expect you to know the logarithm of it. Yep.